All right, hello everyone, and welcome back to the Texas Financial Careers educational modules. My name is Matthew Moskal again. It's been a while since I've seen all of you, and today we're going to take a jump from the thought process we had in our binomial tree case and try to apply it to just some probability metrics, such as what we're going to talk about is the moment generating function. And what the moment generating function is a function of a random variable whose derivatives give the consecutive moments or the expected value measures of our random variable. And this can be very useful for helping describe a distribution. If we can know its moment generating function, we can know its expected value, then we can get its variance, then we can get things like its kurtosis and skewness and so on. And we can use the properties of the MGF as well as to help derive other distributions from it. And so I'm going to formulate the definition of the moment generating function again, and we'll get into the video. So we're going to be talking about moment generating functions. And now, as I said, a moment generating function we'll call it MGF for short, and it is defined or denoted as this, or I'll do the definition first. So it is a function of a random variable x such that the function's derivatives, or the function's nth derivative evaluated at t equals 0 gives the nth moment of our random variable x, and it is denoted as m sub x of t, and is equal to the expected value of e to the tx. Now, so again, yeah, it's this moment generating function is equal to the expected value of e to the tx. The reason we use e to the tx is because we want to build a function that whenever we evaluate it at 0, it produces the moment of a random variable. And a moment of a random variable is simply defined as this: moment of a random variable. A random variable's moment is simply x to the r is the rth moment. So like expected value of x is the first moment, expected value of x squared is the second, variance is the expected value is the second moment minus the square of the first moment, expected value of x cubed is the third moment, and so on. And so watch what happens when we take the derivative of e to the tx with respect to t and do it consecutively. So reason we use e to the tx. So if I do the derivative of e to the tx with respect to t, that is the function e of tx itself times the derivative of the exponent. The derivative of e to the, the derivative of tx with respect to t is simply x. Now, let's evaluate it at t equals 0. This is how you always say evaluate at t equals 0. Then that's equal to e to the 0 times x equals e to the 0 times x equals 1 times x equals x. Now, so look, when we take e to the tx and take its derivative and we evaluate at t equals 0, we get x. And so if we put an expected value around this, we would have expected value x. Now, let's take the second derivative. So the second derivative of e to the tx, well, it's the derivative of the first derivative. So we do d dt x e to the tx. We have this function x e to the tx times the derivative up here with respect to t, which is x. So we get x squared e to the tx at t equals 0 gives us x squared e to the 0, which is 1 times x squared, which is x squared. So you can see, as I said, x to the 1 will give us our first moment, x to the 2 will be our second moment. So here we have the first derivative of the first derivative is x, the second derivative gives x squared. So we get our first and second moments. And if you recall, variance of x is equal to e to the x squared minus expected value x squared. So we can rewrite this a little differently as just being our MGF of x at 0, its second derivative, minus our MGF at 0's first derivative squared. That's how we can write this as well. And so I'm going to show you an example of how we can derive the MGF from distributions, showing the case of Bernoulli and then binomial, and then the normal case. So I'm going to get rid of this. And maybe this as well. And so, as I wrote, for a random variable x, the moment generating function of our random variable x is equal to the expected value of e to the tx. So, for Bernoulli random variable x, we have x follows, here. We have probability big X equals little x is equal to p and 1 minus p when x is 1 and when x is 0. So, if you recall from our early probability days, in order to get, if we want to get the moment generating function of our Bernoulli random variable x, so mxt, well, it's equal to the expected value e to the tx. If you recall, the expected value was simply the sum over all the possible values of x times their probabilities of occurring. And we could also do transformations of this expected value as well. So if we do e to the tx, well, it'll be the probability x equals 1 times the observation of this at x equals 1, so e to the t times 1, plus the probability x equals 0 times the observation of this at x equals 0. That will give us e to the t times the probability x equals 1, which is p, plus e to the 0 times the probability x equals 0, which is 1 minus p. So that's p, e to the t, e to the 0 is 1, so we get plus 1 minus p. Now, let's evaluate this at, let's get the expected value of x. So expected value of x, the first moment, is equal to the first derivative of our MGF at 0. So that is equal to the derivative of p e to the t plus 1 minus p at t equals 0, which gives us the derivative of this is, with respect to t, is just p e to the t. Because with respect to t, this is 0, with respect to t, this is 0. So we just get p e to the t at t equals 0 gives us p e to 0 gives us p. If we do the same, if we do our usual way, expected value of x equals 1 times p plus 0 times 1 minus p is p. They're the same. And we can keep doing this over and over. We can get the second moment, the third moment, fourth moment, fifth moment, and so on. But another important property of MGFs is that they can be used to, you can use the MGF of one distribution to help derive the MGF of another distribution. And we're going to show that with the binomial case. So let me erase this bottom half right here. So, an important property of MGFs, so property, if x1 to x2 all the way to xn are IID random variables, which just means they are independent and identically distributed. So this means x1 is a random variable, x2 is a random variable, and x sub all the way to x sub n is a random variable, and they are independent from one another, which we have talked about in our early probability days, meaning the probability that one occurs doesn't mean given the probability one occurs, it does not affect the probability of the other occurring as well. And given they follow the same distribution, in this case we are going to assume they're all Bernoulli random variables, then the moment generating function of their sum, x1 plus x2 all the way up to xn, is equal to the products of all their MGFs. So this says if we want to know the sum, if we want to know the moment generating function of the sum of all of our Bernoulli random variables, it will simply be equal to the product of all their moment generating functions. And we know that binomial random variable y is equal to the sum of a bunch of independent Bernoulli trials, which we've shown in our earlier discrete probability videos. So binomial random variable y is equal to x1 plus x2 all the way to xn, where x sub I is Bernoulli random variable for I equals 1 all the way to n. So we can figure out the moment generating function of y because we can just plug in this right here. We can find the moment generating function of a binomial random variable just by knowing the moment generating function of Bernoulli random variables, and we're going to show that. So as I showed, mx1, we'll call it, is the moment generating function of our first Bernoulli random variable. Is 1 minus p plus p e to the t. The mx m sub x1 plus x2 all the way to xn of t, we can rewrite this as simply mx or m sub y or here, it might be better to write it differently. If we let y be a binomial random variable, the moment generating function of y is equal to the moment generating function x1 plus x2 plus xn of t, just based off the definition of a binomial random variable being the sum of independent and identically distributed Bernoulli trials. We can use this property and say, okay, that's mx1 of t times mx2 of t all the way to mxn of t for n Bernoulli trials. Because they are identically distributed, all of these have the exact same moment generating function. Thus, we can simply say it's mx1 of t times mx1 of t all the way times mx1 of t, and this occurs n times, so we can just write it as mx1 of t to the n. If we do mx1 of t times mx1 of t and then mx1 of t, you're just multiplying it all n times, so we can just write it like this. Thus, that is the same thing as 1 minus p plus p e to the t times n. That is the MGF of binomial random variable y. Let's take the first derivative of it. If we take the first derivative with respect to t, we get d of dt and y of t is equal to, with respect to t, we have all of this, we do the power rule, do n, bring this to the front, then we have 1 minus p plus p e to the t, subtract 1, based off power rule, n minus 1, times the derivative on the inside, which is p, with respect to t, which is p e to t. At 0, if we plug in t equals 0, we get n, n 1 minus p plus e to the 0 is just 1, so we get p times 1, which is p, n minus 1 times p e to the 0 is just 1. This gives us minus p plus p, so we get 1 to the n minus 1. 1 to any power is just 1 itself, and so we get n times p times 1, which is np. That is the expected value of a binomial random variable. And we can keep going further. We can get the variance and the kurtosis and the skewness and so on. But I want to show the last thing I want to show is the normal, is how we get the moment generating function of a normal random variable. And we're going to show why this, and we're going to show how we can use this in the future videos to extend from the binomial tree case to a normal case, and then to a log normal base, because when it comes to stock prices, they move exponentially, they are non-negative. And so we're going to show the normal case. So we have a standard normal random variable, we'll call it z. mz of t is equal to the, based off our definition of moment generating function, is equal to the expected value e to the zt. Well, from our continuous videos, you get the expected value, that was ugly, by doing this times the function itself. So over all possible values, we get e to the zt times the probability density function of a standard normal random variable, which is 1 over square root 2 pi e to the negative 1/2 z squared dz. And we do that over all possible values. Now, let's try to combine this into something nicer. That will give us integral 1 over square root 2 pi e to the minus 1/2 z squared. We combine these two, and we get plus zt dz. And then we can rewrite this as 1 over square root 2 pi e to the minus 1/2 z minus t squared times e to the 1/2 t squared dz. That is then e to the 1/2 t squared, because we can pull it out since we're not integrating with respect to t, e to the minus 1/2 z minus t squared dz. Now, all we've done here is just shift it over. This is all still equal to 1, because this is just simply the standard normal random variable bell curve, the Gaussian bell curve, which we know all the area underneath it sums to 1. This only has it shifted over, and so we already know that this is going to be 1. So if we then have e to the 1/2 t squared times 1, and we simply get e to the 1/2 t squared as being the moment generating function of a standard normal random variable, and we can take its consecutive derivatives, such as if we take the first derivative, we're going to get e to the 1/2 t squared times t, and if we plug in t equals 0 for that, we get 0, which is the mean, the expected value of our standard normal random variable. And then we can keep going further and find the second moment, and from that find the variance and find that it will be 1, and we can keep going further. But this wraps up our discussion. This is what I wanted to introduce to y'all as being a moment generating function. It is a function of a random variable whose consecutive derivatives evaluated at t equals 0 give the consecutive moments of our random variable of interest. And we saw that we could derive the moment generating functions based off this notion of the expected value of e to the tx. And the reason we use e to the tx is because its derivatives with respect to t will give x e to the tx, x squared e to the tx. Plugging in t equals 0 for all of those gives x squared, x cubed, x fourth, and so on. This is why we use the e to the tx for that. And so we derived some MGFs. The Bernoulli, we showed how we could derive the binomial MGF through some of the properties of MGFs of when cases are independent and identically distributed. And then we showed a case of the continuous MGF for a standard normal random variable. In the next video, we're going to get in how we take the binomial MGF and can use it to approximate the standard normal MGF. And so we can show the link between binomial and normal through a very important theorem called the central limit theorem. And in the video after that, we're going to show the log normal model and how we can use the log normal model to gain insight about expectations of stock prices given they will result in a payoff. And that will ultimately lead us into a famous equation for stock prices and more so option premiums called the Black-Scholes equation. And so this is all I had for y'all. Thank y'all for y'all's time, and I hope y'all enjoyed it. Bye-bye.